Okay, welcome. So this is class 3. Today we're going to prove formally the utility representation theorem for infinite data sets. As you remember here, we have basically a continuum of choices because here we're studying the Euclidean space as our choice set. And of course, we are studying here budgets. Our running example was fractional trading, but in general, right? It can be anything that can be written as a basket of goods, right? Here, we're going to prove theorem 8. So theorem 8, actually, the proof is going to be long. It's going to be a big chunk of the class. I'm just going to state it so we can start. So if a preference relation is basically a continuous rational preference, and we say that preference is continuous whenever if I take a sequence of commodities indexed by n, and xn is preferred to y for all n, and then xn converges in the Euclidean space to x, then it has to be that the limit x is preferred to y. So one counterexample of continuity is lexicographic preference that we studied in the summer. Part of a problem set is going to be to show that the lexicographic preferences are not continuous. With that assumption and rationality, that meaning, of course, that this is complete and transitive on the Euclidean space, then, and this is the important part, there is a continuous utility function u mapping from x to the reals that represents the preference. And when I say represents the preference, I mean that for any x and y in x is preferred to y even only if the given utility function u of x is greater than or equal to utility of y. Okay, so it's a representation theorem. It's two ways. It's an even only if statement. Namely, the only property we're imposing here is that the utility is continuous. Okay. As we progress through the chapter, we're going to add more properties, okay, to the utility function. Right now, this is the only thing we need. And again, right, so what is the difference from the version we proved in the summer? So remember in the summer, I did a little proof where we define a utility on a finite choice set by using the cardinality of the lower contour set, right? So that if you go back to the videos, the notes, you will find that proof. Right now, we're going to do a much more complex proof because the choice set is basically the Euclidean space of size L, right? The positive ortho. So when you have infinite objects, things get harder, right? So the first thing we're going to do is we're going to take a subset of the full choice set, which is going to be for now, right? Just the space of the rationals. So what are the rational numbers? Who can remind me? So the rational numbers, yeah, go ahead.
It's all numbers that you can write as numerator and denominator.
So it's the set of numbers, right? That can be admit a representation of a fraction of two natural numbers, right? P and Q divided by Q, where Q is not 0, right? So this is, of course, the set of rational numbers. Of course, we know that there are reals that are not rational numbers. Classical example, you know, the pi, right? So there is no the pi number, right? 3.414 and so on. So, and then this number, you know, has no fractional representation. So evidently is a subset, a strict subset of the reals. Now, what is particular about the rational numbers? So who remembers what are the properties of this set? So the rational numbers are countable, right? So this is an important property, right? So basically I can make a bijection from the rational to the naturals, right? So basically I can count them. Reals are not countable, right? So this is a known property. So I cannot make a bijection from the reals to the natural numbers. So then the rational numbers are countable. And why this is going to be important? Because we're going to use the countability of this set to be able to make a constructive proof of the existence of utility functions. So here in this subset of the full Euclidean space, I'm going to prove that there exists a utility function that represents the preference. Okay. Now, why I'm gonna do that? So I have to give you the big picture before heading into the proof, you know? Essentially, right, we want to prove that in the Euclidean space, right? You can imagine of the Euclidean space as being basically a liquid, right? So essentially, you cannot really pick any grain from that, right? It's just a liquid. It's essentially a continuum of objects. So we want to prove that utility exists there. So there is no notion of counting, right? So I cannot use this trick where I created this cardinality of the lower contour set. So imagine in this liquid, if I pick any object and I look at the lower contour set, what is the cardinality of that object? Well, you can have infinite objects, right? So cardinality is going to go quickly to infinity. So that trick doesn't work anymore. So it's very hard in general to measure, you know, without measure theory, right? We're not going to use that. So we're a little bit constraining ourselves to not use measure theory, right? So we just try to use a little bit more fundamental math that we know according to real analysis without probability or measure theory. So we want to use basically the countability of a subset of the real. So imagine that you have this liquid, right? And inside this liquid, you mix it with sand. So we're looking almost like the grains of salt inside, right? And then basically we're going to prove the utility representation for this subset, right? Which is the solid part, right? The grains of salt. And then here, you know, once we prove it, then we're gonna somehow expand our utility to cover the whole liquid. That's gonna be kind of the intuition. So we're gonna prove it for the easy set. So the rational set, of course, this is a Cartesian product because there is a superscript L. So it means it's the rational set, but it's not just in the line, right? It's a Cartesian product such that you have L dimensions, right? So the typical element of this set is a vector of which each entry is a rational number, right? And in this set, I'm going to prove that there exists a utility function, right? Of course, notice that the utility adjective has disappeared, right? And this is on purpose because this set, the rational set, is a discrete set, right? So under some topologies, I can make it trivially continuous, but I don't want to do that, right? So continuity right now is not going to be at play. And remember, continuity is a technical thing I'm going to add at the very end. But right now, the only thing it matters is that I'm going to constructively create a utility, okay, in this set. And I'm going to do it in the same way as I did in the summer. So let me first introduce again notation, right? So this set, L of the preference of X, is basically the set of all alternatives in the set of rationals, such that X is preferred to Y. So remember the name of this set? Yes, the lower contour set of X according to the preference relation, right? So this is the same thing we use in the summer, is the set of things that are worse than X according to the preference, right? But restricted, of course, to the subset of the rational numbers, restricted to QL, okay? Understood? Now, this is just a definition. Now, notice that the lower contour set.
Are they necessarily worse? All of them?
By definition, right? So all of Y's that are ranked below X, right? So these, of course, may be different, but are weakly worse, if that's what you mean.
Okay. Thanks.
Yeah. Notice that the lower contour set, because it's a subset of the rationals, is also a countable set, right? So any subset of a countable set is countable. And moreover, it is countably infinite, right? So in fact, we can index it and essentially what we're going to do is take any element in the lower contour set and assign to it an index, right? And the index is going to be called, the collection of all such indexes is going to be called the index set, right? And this is going to be a subset of the naturals, right? And basically there is going to be an isomorphism or a bijection between the lower contour set and the set of indexes. What I'm saying basically is I'm taking elements in the lower contour set and I'm going to number them, right? 1, 2, 3, ... I say ... because this goes to infinity, right? But it still is countable. Now I'm going to create a utility. As before, right? Instead of using, remember previously I was using a cardinality. Cardinality was fine in the summer because I was restricting my attention to a finite choice set, right? So hence cardinality is always well defined, right? But here the challenge is that even if you have a countable set, which is nice, your set is actually infinite, right? So you cannot use cardinality. So what do you use? Well, I'm gonna use a summation that converges. So it always gives me a non-infinite number. And so such a summation, I can choose any I want. So there is nothing particular about this construction. It's just something that works. It's gonna be this kind of summation where I take the sum over the index set, right? From 1 to whatever number. And I'm gonna basically take a coefficient, right? Which is 1 over 2. And then elevate the denominator to the power of the index. And then just take the summation. Expanding the summation, look at it is 1 over 2, right? Plus 1 over 2 to the square, plus 1 over 2 to the cube, until whatever elements I have in the lower contour set. Understood? Right. So in particular, again, I repeat, there is nothing magical about this thing, except that it converges, right? So I can replace by any other summation that does the job, right? That doesn't go to infinity. And the only thing I really need is the following. So I need to prove that if x is preferred to y, right? Then the constructed utility u of x is greater than or equal to u of x is greater than or equal to u of y. Okay, that's the thing I want to show. So let's prove it. Okay, if x is better than y, then remember that I'm assuming that the preference relation I'm using is transitive, right? So then by transitivity, this implies that the lower contour set of x is a superset. That's the symbol I'm using here, right? So it contains the set in the right-hand side. That is the lower contour set of the item y. Do you understand? Why transitivity, right? Remember we did this proof in the summer. Basically, if take an element in the lower contour set of x, right? Then, it has to be that x is better than such an element, right? Then I know by that also the second piece of information is that x is better than y, right? So now I put this together, and it means that this element, is also in the lower contour set of y, right? By transitivity. So together, it means that any element that is in the left-hand side set is also in the right-hand side set, giving me the superset relation. Okay, great. This means obviously by the bijection that the index set that I created, this n set of x, is also a superset of the n set of y. In simple English, it means that there are more elements in the lower contour set of x because x is higher up in the rank given by the preference relation. So, that's why we wanted countability, because it means that in this infinite list, there are higher number below x, higher number of items below x, that numbers below y, right? So it's just a longer tail, right? Even these are infinite tails, the tail of x is longer than the tail of y, and I can measure them, right? And the way I'm going to do it is by means of this summation. Now, remember that any and every term of the summation, right, is a positive object, right? It's all strictly positive, which means, right, that essentially the summation on a bigger set with positive elements in the summation will give me, of course, that the u of x is greater than or equal to u of y. So I have proven the first part of the representation theorem. If x is preferred to y, it means that there is a utility which I constructed, right? Such that u of x is greater than or equal to u of y. So constructively. Okay, great. Now, let's prove the easy part. Imagine now that there is a utility that ranks u of x greater than.
Sorry,
Yes.
Professor, can I interrupt? Sorry, can
Sure.
you again explain this? This means that n, of x, basically the last line. Why is this tails? Can you explain this again?
Yeah, you mean this index here?
Yeah.
Yeah, so remember what is the index, right? So what are the objects in the lower contour set? They are vectors of rationals, right? These are basket of goods. that happen to be fractions, okay? So imagine an example in L equal to 2 with two goods. Imagine bread and butter. Say I have a kilo of bread right now. I have and 2/3 of butter, right? Kilos of butter. So that's the typical vector you can see here. So basically, imagine I choose X being, half kilo of bread and half kilo of butter. That's my X vector. And then I take all vectors that are worse than that, right? So this is the everything that lives in L of X. Okay, great. Now, what I'm gonna do, because this is a countable set, is I'm going to start counting the vectors inside L of X, and I'm gonna number them, right? 1, 2, 3, ... until infinity. Okay, that is the set N. Okay, that is the set N. So now let's go to this sentence, right? So this only means that if X is above Y in the rank, right? It means that there are more vectors below X than vectors below Y. Do you agree with that statement?
Yeah.
Right. So when in the set of indexes, right, in the set of numbers that I was able to count them, there will be more numbers, right, in the N of X than in the N of Y, right? Because the tail is longer, right? So you have more elements, right? That's the only thing I'm saying. Okay.
Thank you. Thank you.
Sure. Now, and the rest, follows trivially. Now let's prove the easy part. So remember, I already proved that when the preference says X is greater than Y, I constructed a utility that says U of X is greater than U of Y. Now, what happens in the opposite direction? Say I have a utility already, and the utility says U of X is greater than or equal to U of Y. Now, this means, of course, that U of X less than U of Y is greater than or equal than 0, just rearranging, right, terms, which means that the following summation is greater than or equal to 0. So this is the summation over the index, the difference between the N of X minus the N of Y. So I take all the indexes corresponding to N of X, and I remove all the indexes corresponding to N of Y. Remember that Y is below, right? So something remains there. And the only thing I'm saying basically is that this means that essentially, right, X has to be strictly rank above Y, or, for the case of indifference, when the two lower contours are the same, X is indifferent to Y. So there are two cases, right? The index set is the same, the summation is empty, and this is 0, or the index set is a strict superset, in which case this is a positive number, and in which case X is strictly greater than Y. So basically I'm able to prove the opposite direction. So this is an if and only if statement. The U of X that I constructed represents the preference relation. And I have basically done the first step towards my main theorem. So now, again, here there is an example. Hopefully that illuminates the question by Irina, right? So imagine this vector x1, x2, x3, ... This is the vectors that I described of bread and butter of fractions, right? And now the corresponding index is 1, 2, 3, 4, ... right? And there is a bijection. So for each vector on the left, there is an index number on the right, okay? So 1 to 1. Okay, now, so this is just an intermediate result. So we're not done yet, because the choice set of interest is the Euclidean space, RL, the positive sign, right? So we're not done yet. So remember the analogy that I told you, that we started proving the utility in the grains of salt. Now I'm gonna fill it with liquid, such that, you basically are gonna fill in the spaces. So this is an extension theorem. And now you're gonna use basically the non-constructive part. I'm gonna use two proofs. The first one is a little bit informal. It's a little bit hand-wavy, but it gives you some intuition. And then I'm gonna do a more formal construction, right? So in the first part, I'm gonna be a little bit hand-wavy, but I'm gonna give you the intuition of what we're gonna do. Even more intuitive, I'm gonna tell you that we're gonna start with the utility we constructed in the rational set. And essentially, we're gonna take the limits of this of sequences of rational numbers, and the sequences of rational numbers are gonna go to fill in the blanks, essentially, right? So I'm going to imagine, for instance, I want the utility for some vector that contains a pi quantity, right? So this is not rational. So I'm going to take a sequence of rationals that converges to pi. I know this exists by results in real analysis, and of course I am going to extend these results for vectors. I'm going to take basically the limit of that, and then I'm going to use the utility constructed for the rational space, and I'm going to extend it in a particular way to cover the blanks in the reals. So this part of the proof is, again, more existential, not really constructive, but let me go through it. Of course, stop me if you have questions. So from the previous representation theorem, I know that a rational preference defined on the QL, so the set of rationals, have a utility representation U of QL to the reals. In fact, I can also think of the same utility restricted to 0, 1. Because remember that I constructed using these telescopic summations, right? And they are bounded below by 0 and above by 1, okay? So that doesn't matter. Now, know that Q is dense in the reals, right? And also QL is dense on RL. So this means that any point in X is either in Q or there is a sequence Xn such that Xn belongs to Q, that it converges to X in R. And of course, Xn goes to X, then X is in the reals. So that basically means to be dense. So I'm just going to describe what it means to be dense for the R and Q without the L, but you can basically extend the same definition for the Cartesian space, the Cartesian product space, okay? So again, this is from real analysis, nothing fancy. So Q is dense in R. Basically, if any point in X is either in Q or there is a sequence in Xn belonging everyone is a rational such that it converges to X, right? And it's in the reals. So essentially, you know, there is a famous chapter in real analysis where you do construction of the real line, right? So you start with a Q, the set of the rational points, and then you start taking sequences such that you fill in the blanks and you create a real line, okay? So that's the constructive creation of the real line. So essentially here I'm saying, look, I already have the real line, and then I have the rationals inside. The rationals are dense in the reals because either any point in the real line is in the rationals or there is a sequence of rationals going to the point in the reals, okay? Do you understand? So a graphical way to understand this is, again, is if you have a mason jar, right? Filled with sand, and then you pour liquid in it, right? You're gonna completely fill it, right? The sand is the rationals, right? And the liquid in between, you know, filling everything, you know, is the complement of the rationals. And together they're gonna form the reals, okay? So that's basically it. If you mix it, right, that's the reals. So now, okay, so now what I'm gonna do, remember that I already constructed a utility for the rationals, right, for the sand. So a first try would be to define a utility V in the Euclidean space. So actually in the reals, in the following way. So here is the hand-wavy part. So take Vx to be the limit, right, of the image of the U of Xn. And then essentially what here, of course, this is not well defined, you know, it's just an intuition. I'm gonna define it formally in a second, such that Xn goes to X. And then remember that Xn, I can pick it up or choose the sequence such that it is better than the previous element in the sequence. So Xn minus 1 for all n. And this means that this sequence is increasing, right? So it's an increasing sequence. And remember that the utility lives in 0 and 1. So it's bounded, it's a bounded sequence. So it's a convergent sequence, right? So essentially I'm creating an image, a sequence of images. So U of Xn that is increasing and is bounded. So it's going to converge because it's Euclideans, and there is a limit, and the limit of such sequence is going to be defined as the V of X. So the issue here, which makes it a little bit hand-wavy, is that you have to assume that you can pick these increasing sequences, right? But, you know, other than that, you know, it's a good construction. And essentially, because, and here is where continuity kicks in. Remember what was the definition of continuity? That essentially I was saying that if I take any sequence of alternatives, Xn and Yn, such that they are ranked Xn is better than Yn, if I take limits and all of them go to X and the other go to Y, then in the limit, the preference relation will preserve the ranking of the limit items, making basically that X is better than Y. So utility will guarantee that this construction makes sense, and in the limit, nothing fancy or weird happens, right? Such that you can extend this naturally. So utility, just to remind you, if you have a preference relation that fails continuity, the utility representation may not exist. And again, lexicographic preferences are such an example, right? Continuity here is where it allows me to make this construction happen, right? So only with continuity, I can extend the construction I did in the rationals to the reals, right? Because by taking limits, right, I have to ensure that the limits preserve the preference, okay? So that's why I need continuity. So continuity is essential for this construction. Note that this is in contrast with our result in the summary, where for a finite set, you don't need continuity, right? So continuity doesn't matter. And for a finite set, any complete and transitive preference relation admits a utility representation. This doesn't happen for the Euclidean space where you need continuity, okay? Now, so I did this construction, as you can see. Now, importantly, imagine I don't want to take these sequences that are increasing, right? I don't want to use this axiom of choice again. I want to do it more constructively. Then I can use basically a construction by Rubinstein. These are the notes in Rubinstein's, the theories in NYU. Another candidate for a utility function that represents the preference. Essentially, I'm going to call it Wx. And this is just the supremum of all u of y for all, basically, remember they are fixing x and you're taking the supremum over all y's in the rational QL, such that y is worse than x, okay? So what this, Rubinstein was doing essentially is using the utility I constructed in the previous term, right? In the previous result for the rationals, I have a collection of utilities. Then I take basically the lower contour set of x, right? And then I take the supremum over the utilities in the lower contour set, okay? And that is always well defined. You don't need to take sequences that are weird. You don't need to assume anything here. The supremum in this case always exists. So it's a nice result because the u is bounded. Remember, lives between 0 and 1. So then this is well defined. You get it Wx, and it's very easy to basically show that this thing represents the preferences, right? So this, you can do it yourself. It's very easy. And continuity from this construction follows from something called the Breu's gap theorem. So this construction is of course highly technical. Usually it's left for a field course, right? When you study decision theory V1, and then you can study the Breu's gap theorem. But at this stage, right, we're just gonna show that the constructed utility I did is gonna be in fact continuous, right? And continuity follows from a technical result due to the Breu's, okay? So for now on, remember basically the intuition of this part. Take the construction from the rationals, extend this to the Euclidean space using a supremum, for instance, operator. And once you do that, you get yourself a utility representation in the full Euclidean space. And this utility representation happens to be continuous, right? It happens to be, represent the original preferences, okay? Importantly, this works under the assumption of continuity of the rational preferences. They need to be continuous for the infinite set. They don't need to be continuous for the finite set, okay? Important. So agree? Everyone is happy with the construction? And then we can move on. I'm gonna stop for questions.
So this is the most relevant case, right? Because it will be always infinite. I don't think that the whole Euclidean space, but at least the non-negative reals, right?
Yeah, so remember in this proof, we never used really the fact that, so actually the same proof can go for the whole Euclidean space, allowing negative objects, right? So we are just restricting, so the proof indeed, as Martin mentions, right, doesn't use the fact that you're positive, right? So the positivity is just a restriction we're imposing here because we want to talk about positive quantities, right? But of course, there are cases where you need to redefine the theory for negative quantities, and this construction will go well. So nothing changes at all, right? The only thing that matters here, what it changed from the summer, is that now you have an infinite set, right? As opposed to a finite set. So when you go to infinite sets, the utility representation is harder, and you have to be careful. But usually the trick is you use a dense subset inside the set of interest, right? And you prove the utility there using these ideas of counting, right? Because it has to be a countable set. And then you extend it using the properties of the topology and basically the fact that it's dense, okay?
Okay, so if we restrict to a non-negative part or set of the Euclidean space, we will need this theorem, we will need continuity, and that is what is.
Continuity arises because the set is continuous, right? It's infinite, okay?
Yeah.
It's infinite or continuous. It's an infinite set. That's the important thing,
Perfect.
okay?
Great.
It's a continuum. Okay, great. Any other question?
Yes. Can we think of these two approaches to the proof sort of as the reverses of each other? Because in the first case, it looks like we really carefully set up that the rationals are continuous in the reals, and then using that, we constructed utility and found the utility and preference relation. So it was kind of like first continuity of rationals to reals, then utility, whereas in Rubinstein, it's kind of the reverse. First, we find a candidate utility function, and then sort of as an afterthought, we say, by the way, it's continuous because we have Debreu's gap theorem. Something I observed through your explanation, does that sort of sound about right? You might think of them as one as the reverse of the other, of the way of getting to the same result.
Yeah, that's a good way to see it, right? So because in the first proof I did, right, I essentially was using the axiom of choice. So assuming there exists a sequence, right, and using continuity to complete stuff, right? In the other is more direct, right? So it's a more constructive proof. So just use the existing utility of the previous lemma, and I take the supremo, and then I'm done, right? But if you think about what's going on there, right, essentially we're taking the supremo, right? You're thinking of sequences, right? And then once you do that, right, instead of assuming continuity and using it, right, here instead I get continuity by the Debreu's gaps theorem. However, both Rubinstein proof and my proof use the assumption of the continuity of the preferences, right? Yeah, okay, good. Any other question? Nope. Okay. Yeah, so one important thing about theory and this kind of core courses is that some results, right, give you a glimpse of what it means to do, for instance, pure theory. So most of you, if you become applied, you become an applied guy, you know, a macro guy, or structural IO labor, you won't be doing these really representation theorems, right? So you won't make a living out of doing those representation theorems. However, at this stage, you know, you are going to use assumptions such as utility and the fact that there exists a utility. So now somehow the idea, you know, is that you now know why you can do it freely. And the important thing, right, the thing you should remember, if you remember one thing, is that when you move to basically infinite spaces, the preference relations are more general, right? And for instance, remember the lexicographic preference being one example, you know, they always exist and are well defined, even in infinite sets. So these are preference relations, while utility functions are more particular because they need the additional assumption that preferences are continuous. However, continuity is really a technical assumption, as I mentioned, and it's not really testable. As I told you in the previous class, there is no experiment that can actually ensure test, you know, the continuity assumption, right? So in that sense, you know, the gap between the existence of a utility and the preference relation is really a technical gap. So now you know this, right? But you also know that in order to make a model consistent, right? If you use utilities, you will be ruling out things such as lexicographic preferences, right? So you have to be internally consistent, and this is something now you know. So lexicographic preference and any other preference that is not continuous, right, simply cannot be represented by a utility function, right? So utility functions in that sense are theoretically more restrictive, right? Now in practice, they are not really because continuity is technical, right? But in the world of infinite data and in the theory world, utilities are always more restrictive than preferences. So preferences are just more robust and you don't need continuity and so on. Okay, Now, okay, so we know the price. The price is small, so we're happy with using utilities, okay? Now let's move to the utilities. So now the chapter is gonna become more practical, okay? So for the first time, we're gonna all the binary preference relations and then go straight for the utilities, okay? And why we're gonna do this? Because utilities are more tractable, right? You can optimize utilities, right? You can use calculus, you can use optimization, you can program them in a computer, you can maximize in a computer a utility function, right? Using preference relations is just computationally harder, given current technology, right? Maybe that changes in the future, but right now, maximizing utilities, doing model with utilities is just nicer and more tractable, okay? So once we have paid the price that we have to assume continuity, we're fine. And now we're gonna start basically making models. So let's start with a utility maximization problem, okay? We assume that the utility is continuous, as we said before. The Euclidean space is the real lines. We're gonna remove negative quantities. For now, utility maximization problem is the following. Maximize the utility with the constraint that you have to be positive. So just to make it explicit, subject to the inner product of P times X less than equal than W. So remember, W is a scalar. Prices and X's are vectors. The transpose symbol basically means that you are taking the inner product of P times X, right? So in other words, for the case of two goods, what I'm doing is basically taking the price of good one, multiplying it by the quantity of X1 plus price of two, quantity of X2. And this is a scalar, is less than equal than the scalar number W, right? So it's a linear constraint. Alternatively, right, I can also say X has to be in the budget set, and the budget set is, of course, the one we defined before, okay? Proposition 7 is a simple result for warming up. It says if prices are strictly positive. So this symbol in Maskell L with a double greater than 0, it means that you are strictly greater than 0. Because it's a vector, it means that every entry is above 0. If this thing has just a greater than or equal to, it will mean that there can be some entries that are 0, right? And some, of course, there has to be entries that are positive. Here, it means that every entry is positive. And the utility is continuous, then the utility maximization problem has a solution. So here, of course, the proof is gonna leverage on some knowledge that you're gonna get from the math class, right? That essentially, with Maria or whoever is teaching you the math class, you're gonna basically do the proof that the budget is in fact a compact set. And you have to do some technical work there because you have to be careful with some boundaries and so on. So formally showing this is a compact set will be done in that class. But after doing that, right, so I'm gonna take it as given. Basically what I'm doing is I'm maximizing the utility function, which is a continuous function on a compact set, okay? And this is a result, you know, from math, from real analysis when you do that. And essentially this compactness means that you're close and bounded and you're maximizing a continuous function on a close and bounded set. It basically means that there exists a maximum. And in fact, there is something called a maximum theorem, you know. There's many results in real analysis that shows that with different levels of generality. And in general, I know that maximizing a continuous utility function in a bounded and closed set will deliver a maximum, right? So there exists a maximum, okay? So that's it. Now, important commentary. So here, you know, the crucial object here is the utility. Remember that the utility already has embedded in it completeness and transitivity, right? So when you have a utility, you're assuming already you have completeness and transitivity. You know that, right? On top, you're adding continuity, right? So with the technical condition of continuity, completeness, transitivity, and the fact that the budget is compact, closed, and bounded, now you have a maximum, okay? Now, why you should care that there is a maximum? So having a maximum means that the model you are building up is internally consistent. So tomorrow, say I hire you for a consultancy, right? And I say, okay, look, I want to predict what are gonna be the purchases of consumers if I basically change my prices from this particular good, you know, 20% up. So I want to increase my profit, but I want to know, what is the prediction? What is the demand for this new price? So when you do that, basically you're asking, first of all, you're asking how much, right? But the model that you're building has to at least be sure that you can predict at a new price, okay? So the fact that you can predict at a new price is basically an internal consistency check. Now, just to make things clear, not every model of behavior is guaranteed to have a maximum, okay? Disclaimer, many models, for instance, of behavioral economics that are dissing completeness and transitivity may not have predictions for every new budget. So in particular, existence is not longer guaranteed. Existence is very delicate and happens here magically because of the combination of completeness, transitivity, and continuity, plus boundedness of the budget. If that fails, your model also can fall apart. So this seems actually trivial and almost mechanical, but this is work you have to do. So if you're hired as a consultant, you have to first, check that your model is producing a maximum, okay? Now, luckily for you, if you live in the world of rationality and you assume continuity and you're doing a linear budget, then things are nice. And you're gonna get a maximum, okay? Guaranteed. Not necessarily a unique maximum, but at least a non-empty solution to your problem. Got it? Okay, so this again, we're borrowing from math. Question here. So imagine I change your problem, and instead of having a linear budget, I give you a non-linear budget set. Okay. Then can you tell me the conditions on the non-linear budget such that you still have a solution, and the conditions, of course, on utility? Who can give it a try? So just give me conditions on the utility and the non-linear budget, such that I still can guarantee that there is a solution to the maximization problem. So, Jake, can you hear me?
Yes, I hear you.
Yes, can you give it a try?
The way that I was thinking about it was just closedness and boundedness for that would be for the constraint, right? So
for the non-linear budget, right? So even if your budget is non-linear, right, you can still constrain it to be close and bounded, right? You have to be careful that the property of being close and being bounded, it still holds. So that's great, Jake. Thank you. So, and of course, you keep the utility being continuous, and you're still gonna get the existence of a maximizer. So again, linearity here of the budget line doesn't have anything to do. The important thing is that you are close and bounded. Okay. So great, Jake. Thank you. So again, this becomes important, because when you become applied and you are working on your thesis and your dissertation, things get hairy quickly, right? So imagine, for instance, you are studying the impact of a new, income tax, right? Now that's going to change, your incentives, your budget. For instance, if you're thinking about labor supply, so usually taxes are non-linear, right? So usually, as you start earning more and you pass certain thresholds, you are actually taxed more, right? So that's basically something that creates a non-linear budget. That's a classical example of a non-linear budget, right? So, and of course, there are many other cases where budgets becomes very complex. Another example where budgets becomes very complex when you don't have just one linear budget, and you have many linear budgets, right? So for instance, you can have different categories of goods, and you have a budget per category. For instance, you have a budget for food, you have a budget for recreation, and so on, right? That's what is called for instance, a mental budgeting model. Thaler, the famous Nobel Prize, did that model. So instead of having one budget, you have multiple budgets, right? In that case, the final budget is the intersection of linear budgets, right? It happens to be a convex set, but as long as it's convex and bounded, you're going to have a solution, okay? So in other words, I just want you to have clear that, existence basically fundamentally is not about linearity or the fact that there is one budget, but rather about the compactness and boundedness of the restriction set, okay?
Sorry, can I just add? So would it mean that because now we are with Maria, we're learning about this, what's called the qualification, constraint qualification condition, that it should be full rank. Is it the same thing is to say?
Yeah, so that's in the Karushkin-Tucker world, right? So essentially,
Yeah.
that's a way also to ensure with a more
Yeah.
direct way using first order conditions existence. Yeah, but so that's perfect. Here we're a little bit more abstract because this may go beyond that, right? And we're just saying, look, as long as your cloud unbounded and your utility is continuous, we're fine. In the case of Maria, sometimes you can also cover cases which are not covered under this theorem, but you can use the constraint qualification and others, right? So these are complementary tools, right? And yeah, of course, learn them all. So that's essentially, that's the first step in any model, checking that there is a solution to it, which means internally consistent. But so my answer to you in summary. So this is a classical theorem, which uses a more, topological, if you want, existence theorem. You just have to check your closed and bounded, right? But usually checking that is complex. So sometimes you can use a more direct approach that is friendly computation, like the Karish-Kuhn-Tucker and constraint qualification, and that's fine. And sometimes also you may fail to be closed and bounded, but constraint qualifications could go through still. So these, I would say, are complementary tools to show existence, right? Again, any existential claim is, of course, a sufficient condition. So even if my conditions fail, there still may exist. Do you understand this, right? These are sufficient conditions. So imagine there is a problem where my budget constraint is not closed or not bounded, right? Then it may or may not exist a solution, right? So these are sufficient conditions. So in that case, you have to go to other tools to try to see if there is a solution to your problem. Okay, so that's something you have to do. Now, my message to you is: don't assume without proving that your problem has a solution, right? That can bring you trouble, right? So you have to be sure that this is in fact at work. Okay. Any other question? No. Okay, so proposition 8. Now, in Mas-Colel, in this chapter, remember that Mas-Colel calls this Walrasian demand correspondence, but suddenly, in some point in the chapter, Mas-Colel starts naming the demand correspondence as Marshallian demand correspondence. And the difference between the Walrasian demand correspondence and the Marshallian demand correspondence is that Marshallian demand correspondence comes from utility maximization, right? It's a little bit confusing, right? But this is due to historical reasons. So the Marshallian demand correspondence has a special status because this is generated by a rational agent, right? So that's just that you read Mas-Colel easily. So in general, right, we're going to say the Marshallian demand correspondence, which is the set of maximizers, right, generated by the set of maximizers. So the utility maximization problem is non-empty, so it has a solution. It's compact value, and it's upper continuous, right? Which is the definition that I asked you to check Mas-Colel. And moreover, right, we're going to define an object called indirect utility, which is is a function of prices and income, and is equal to U of X evaluated for any item inside the demand correspondence in the image. So take a maximizer, put it inside the utility, and tell me how much utility did the consumer derive from the optimal consumption, right? So this is the indirect utility, and this is called V of PW. So these two objects, the second object I introduced is going to be continuous, right? And these properties, namely, are a restatement of a little bit what I said before, plus additional properties. And this is a consequence of a famous term called the Berg's theorem. And the Berg's theorem basically says that if I now check how my solution changes with the parameters of the problem, what are the parameters of the problem? The parameters of the problem are prices and income, right? As I change price and as I change income, I have to check how much P changes and how the demand is going to change, right? And then as I change income, I'm going to change how the demand is going to change. So the demand turns out that irrespective of the price and income level, is always going to be non-empty. It's always going to be compact value. So remember that I told you that the image of the demand correspondence is a set, right? The set is guaranteed to be compact always. And on top, the demand correspondence is going to be upper continuous. So remember that this means that in the image, and I take a sequence in the input, right? And then this converges to X. And then I take an image, I take a sequence in the image, and this converges to some point. In the limit, it has to be that the limit of the sequence of the images has to be in the demand correspondence of the limit of the inputs, P and W. So this is, of course, the definition we just did. So this is telling me basically that as I move the parameter P and W, the demand correspondence is going to change almost continuously, right? Every image is going to be compact, closed or bounded, so it's never going to go to infinity, right? And on top, it's always going to be non-empty. So this is the 3 guarantees I'm giving you, which is not much, right? It's just technical things I'm getting for internal consistency. I'm not giving you much. And finally, the indirect utility happens to be continuous, which means basically that the welfare I derive from consuming, right? As I change continuously price and income, it's going to change continuously as well. So it's not going to jump suddenly. So imagine my price changes from $1 to $1.01. My welfare is never going to change from 10 to infinity, right? It's going to change continuously, right? So that's what I'm going to tell you. So again, these are all internally consistency checks, nothing behaviorally meaningful. That's what I'm going to make clear at this stage. So if you're expecting me to tell you the utility, the man is doing something fancy that I can actually see as an empirical implication of the model, this is not it, right? This is just a technical guarantees for internal consistency, right? And these are basically implications from this theorem from math called the Burke's theorem, right? Now, as other math results we use in the class, we're not going to prove those results. We're just going to be users of those results, right? So the Burke's theorem tells you that if you maximize a continuous utility function, continuous function in general, on a correspondence. So here, remember that as opposed to the previous result, I'm allowing prices and income to change, right? So instead of thinking of the budget constraint as a fixed object, here I'm thinking of the budget correspondence. What is the difference between the budget constraint as a fixed object? When in the previous proposition, P and W are fixed. Here instead, I'm thinking of P and W as moving, okay? They are changing, that's the difference. Now, because P and W are changing, I have to think instead of the budget constraint, I have to think of the budget correspondence. So I already basically introduced the budget correspondence previously, in the previous class, in fact. The budget correspondence is nothing else than this object here. For every P and W, I'm giving you the budget constraint, right? So what is the image of the budget correspondence? Fix a P, fix a W, and it gives me the budget constraint. As I move P and W, it gives me the new budget constraint, right? So this is the budget correspondence. Now the budget correspondence is a continuous correspondence. This is a bold claim, right? It's a continuous correspondence. Again, I'm not going to prove it, right? This is usually done in the math class, but you basically have to check there, and this is an exercise that is always done there, that the budget correspondence is a continuous correspondence. I already defined what is a continuous correspondence in the previous lecture, so you can check. Once you have checked that, now I'm ready to apply the Burke's theorem. So as you can see, so we're not really doing math, right? So we're just being users of a math result, right? So the Burke's theorem assumes two things: utility is continuous, so that we take as given. And second, the constraint correspondence is a continuous correspondence. That I haven't proved, right? So I'm just taking this as a true statement. And once I have, under that knowledge, I'm able to apply the Burke's theorem. So the Burke's theorem tells me now, right? And here, actually, I did part of the proof of the continuity of the budget. So I'm gonna do it in a second, but I'm just giving you the full picture. So once you have the continuity of the budget correspondence and the continuity of the utility, immediately you get that the maximizer or the Marshallian demand correspondence is non-empty, is compact value, and is upper continuous, right? And the indirect utility is continuous. So all of this follows from this Burke's maximum theorem. And in fact, it doesn't only work for utilities, right? So replace utility by any function that you're maximizing, right? You're gonna get the same properties, right? It can be any problem that you're facing, okay? As long as the budget constraint is continuous, you're gonna get this. Okay, so it doesn't essentially means that it only applies for utility maximization. Here, our interest, of course, is utility maximization. Now, so I'm gonna do part of the proof of continuity. So remember the definition of a continuous demand correspondence, continuous budget correspondence. In general, any correspondence can be continuous or not. We have to check if they are. We're gonna do part of the check. So take here a sequence of inputs. So Zn. Zn is a sequence of vectors of Pn and Wn. So just a sequence of prices and income. Now assume Zn converges to Z. Okay. Now we want to prove that in a set notion of convergence, the image set of the budget correspondence according to Zn converges to B, or the budget at the limit set. So remember, this is convergence in terms of sets, right? So it essentially means that there is a sequence of sets that essentially in the limit converges to the set that is the target, B set. So recall that the budget correspondence for the PN sequence, PNWN sequence, is essentially all the items in X for which the X's are inside the budget constraint, given that Pn and Wn are characterized in the given budget N. Now, first assume that Xn that belongs to this budget image and Xn to X essentially is converging. So these are elements on the image. So these are demands instead. So for each Pn and Wn budget, there is an Xn demand vector, right, inside the image. Now take a sequence of them and they go to X, right? Now we prove that X belongs to the budget at the limit set, okay? So now remember that if Xn belongs to the V of Zn, it must be that Pnx is less than or equal than Wn for all n. Now if we apply limits in this inequality, because it's a weak inequality, we know limits are preserved with weak inequality. This is not the case with a strong inequality, but with weak inequality, this is true. So now we know at least that, of course, this object here is going to be inside the budget, right? And of course, you also know that the utility is continuous, right? But at this stage, we're not using that yet. So we're just showing that it's gonna be on the, at least a point inside the V of X. Now this is showing, of course, that whatever limit of the V, P, and Wn is gonna be inside the V of set, right? So the limit set. Now, in general, right, we conclude that we take that Xn goes to X, and we have that the sequence of P and Wn goes to PW, then X belongs also to the limit correspondence, right? So this just so one part of it, right? And the full proof, essentially, right, it means I have to reverse it. So now we prove that if X belongs to the limit, right, then there exists a subsequence of the sequence set N such that there exists an XK going basically belonging to this image of the subsequence set N comma K such that XK goes to X. The proof here is more complicated because this is a sequential extender, right? So there has to be this subsequence of objects that converges. And you can find the full proof in this link that I gave you. This is from Kim Border. And of course, this is beyond the aim of this class, because this is not a math for econ class. This proof of the opposite part of the statement, the two arrows proof, is a math course class. So go here to the, if you're interested for the second part of the proof, and then you can find why this budget correspondence is continuous. Now, with that in hand, we apply Berg's theorem to obtain our conclusion. Again, so what we're doing here, is a classical example again of the use of mathematical results in the class. We take, high-level mathematical theorem, Berg's maximum theorem. Berg's maximum theorem requires continuity of the budget correspondence and continuity of the utility. Continuity of the budget correspondence is the only thing we need to prove. We check it, right? So in a full paper, in a second year class, I will do the full proof. Here, I'm doing the proof of the part that is simpler. And then the second part, I'm leaving to you if you want to go deeper into it. But I'm never going to test you on that, right? On the full construction of this thing. So once you do that, right? You know now that the budget correspondence is continuous, and I can apply the Verx maximum theorem. The Verx maximum theorem essentially guarantees that this statement is true, and I repeat, the Marshallian demand correspondence is non-empty, compact value, and upper continuous. Okay. The important things, the demand correspondence doesn't have a guarantee to be unique, right? In general, it's a set. It can be a set. It doesn't have a guarantee to be convex, right? So at this stage, for instance, you can have disconnected intervals as the solution of the utility maximization, right? So this is, for instance, compact value, as long as the intervals are closed and bounded, but they are not convex. So you, at this stage, without any further assumption beyond continuity, you can get actually non-convex demand correspondences, right? So which can be very weird. So I'm basically essentially telling you that the demand correspondence this stage is too general. It's very general. And the only property that it really has is that it's apparently continuous. So it has some level of continuity, right? It's not blowing up in general. So that's it, okay? And the indirect utility being continuous, essentially, as I told you, means that the welfare that you derive from consuming, if you're a maximizer, is not jumping, right? So it has to change basically continuously as you change prices and income. But it's nothing else, nothing striking, right? So this is Verx maximum theorem. Okay, great. Now, so right now, we're gonna get to something more fundamental, right? So these properties are nice, are internal consistency checks, but also are not very useful in general for trying to make prediction about human behavior. So we're gonna go deeper and try to add more assumptions, right? So one assumption that we're gonna use a lot is what is called local non-satiation, right? Local non-satiation says that we have a preference, and we say that this preference is local non-satiated whenever for any x in the choice set, and for any epsilon, which is a small number that is positive, there exists another commodity bundle y that in the norm of, you can think of this as the Euclidean norm, right? Is close enough to x. That means that the norm of x minus y is less than epsilon for any epsilon that you pick. It can be arbitrarily small, such that y is strictly preferred to x, okay? So at this stage, right, I'm gonna basically do some graphs, so you can see that you can also get this from Masculel. He has some interesting examples of locally non-associated stuff, but let me do it here as well, so, such that we are on the same page. Okay. Can you see my screen? Okay, good. Yeah, good. So let me do an example of something that is locally associated, right? So essentially, right, I can have these sort of preferences. And these preferences go in this way, such that the utility of this level, right, 3, is basically dominated by utility of 2, and the utility of 1 is greater than utility. So basically the inner circles give you more utility because, you know, there is association point. So x star, you know, is the best possible object, okay? So essentially, usually these utilities can be written as utility of x is equal to minus of the norm of x minus x star to the square, right? So these are called associated preference. So tell me, you know, I am telling you these are associated preference, right? So they have to fail local association. So why do they fail local association? So essentially, right, take this x, right? And there is no x, there is no y in the vicinity, right? Epsilon, or any epsilon positive, right? That y is better than x because x is the best object possible, right? So at this point, there is nothing nearby that is better. Do you understand? Okay. So this is a counter example. Okay. Now let's go to another example. So I'm going to do indifference curves now. I have two goods, x1, x2, and my indifference curve is going to be like this. So this is kind of a weird indifference surface, right? So it has all this area here. So take, for instance, an object here, X, right? And now, notice that within epsilon, there is all Y's here are Y indifferent to X, right? For all Y such that Y minus X less than epsilon, right? So essentially, right, in this part, there is always something that is indifferent, right? Within a small epsilon. So what local association is really doing is ruling out, of course, association points, but also is ruling out thick indifference curves. So in fact, a local association will basically, and now I'm going to give you an example. So local association is basically giving you these nice indifference curves, right? Where there is no area to them. So essentially take any point here, right? X, and you can draw a ball of ratio epsilon, right? And you can always find here a Y that is better than X, right? So this is now an example, right? As opposed to a counterexample. Now, another example. So again, local association doesn't mean monotonicity. And this is an example in Mascolel, right? You can have this, he always likes this wavy indifference curves, right? So for instance, take here something X here, right? And now, basically you can draw a ball here, right? And you can see here that basically by doing these indifference curves, right? You can find something that is better than Y, right? So for instance, in this case, something that is better than Y, better than X is, for instance, this Y here, right? Right, and this is better than that. Okay, so again, so local association doesn't have anything to do with convexity. Is weaker than monotonicity, right? The fact that more is better is a very simple and minimalistic property, ruling out essentially thick indifference curves and association points. Okay. This is a very minimal property. So everyone understand what is local association? Okay, great. So let me share again the screen. Okay, so a local association, right, is gonna, however, be super important in what follows. So there is a little, very secret of rationality. So, imagine you have a data set and you want to test whether this data set of demands comes from a utility maximization, right? So if you don't assume local association, there is a trivial way to say everything is rational. So basically you assume you have a utility function that makes everything indifferent to everything, right? Such that any data set you see, basically say, this comes from an agent that is indifferent about everything, right? So whatever you see basically is a random realization, is a tie-breaking rule. And because tie-breaking rules are completely arbitrary, anything goes, right? So local association, essentially, is ruling out the triviality of utility maximization. So it's eliminating the fact that you have indifference curves that cover everything, the thick indifference curves. So you need local association, right? Local association is important because else rationality is trivial. Okay, we're gonna make this even more clearer later, but right now, have in mind that local association is important empirically, right? Because you're ruling out the fact that you can make everything indifferent to everything, right? So local association is ruling out that, okay? Assume that the Marshallian demand, what is Marshallian demand? The demand that maximizes a utility, right? Is generated by maximizing not only a continuous utility, but also a local non-associated utility function, right? So on top of continuity, we're adding local non-association, more assumptions, right? Then, of course, if you assume more, you get more. So then the demand correspondence has more properties. First, is homogeneous of degree 0 in P and W, right? So that means that if I scale up prices and income by alpha, right? Now I'm gonna get the same demand function later, right? So this means that if I double the prices and I double the income, then I'm gonna get the same thing here, XPW, right? Now for any scalar alpha. Now, well, the second thing I get is the Walras law. So I'm gonna ask you to prove the second statement right now, and I'm gonna ask one of you. So I want you to prove that Walras law, meaning that the demand or the solution to the optimization problem lives not inside the budget constraint, but in the boundary, right? So the constraint of the budget constraint holds with equality instead of a strict inequality, okay? Holds with equality. So, and finally, right, if we add on top of local association, we add that the utility is quasi-concave, or the preference relations that are being represented by such utility function is convex. I'm going to tell you what is a convex preference in a second, but I already told you actually at the beginning of the class in the previous lecture. Then XPW is convex value. So I explained what is convex value. It means that the image of the demand correspondence is a convex set, right? Take any 2 points inside the image, and then the linear combination of them has to be inside the image of the demand, right? So in the case of just one dimension, it has to be a connected interval, right? But and a counterexample is a disconnected interval. And moreover, if the preference is strictly convex and the utility, the counterpart in the utility world is strictly quasi-concave, then the XPW is a single element. So finally, we have a condition that is sufficient to tell me that I'm gonna have a unique maximizer, right? And what is such sufficient condition is that you have a strict quasi-concave utility, okay? But before going there, let's use our brains to try to prove formally that if you have a utility function that is locally non-associated and you maximize it in a budget constraint, you're going to satisfy property 2, Walras law, that the solution lives in the budget frontier or exactly with equality, right? How will you prove it? So I'm trying to prove it right now. I'm going to ask you in a second, okay? Then we're going to try to do it.
Do we need
together.
to do like a formal proof or the intuition?
I mean, like right now you can do it orally. So let's do like the intuition, and then we can try to write it for me.
Yeah,
okay?
Because of non-association, I think that there is always a different consumption basket that is preferred to any consumption basket. So if we are if we have like an excess of income, so that we are spending in consumption, but we have a remaining income that is not spent, there is always a consumption basket that is preferred to what we are consuming right now, so that we could be reaching that point. So we still be like moving forward so as to reach the maximum point which is allowed by our budget constraint.
Yeah, I think that's a good intuition, and right now let's formalize, right? So assume towards contradiction that you have an X that is in the demand, Walrasian demand, Marshallian demand correspondence, and U is locally non-associated, right? Basically, I have that this X is such that P times X is strictly less than W, right? Towards contradiction. So essentially, I have a maximizer that is not in the frontier, is inside. That's my premise. Now, if that is the case, by local non-association, right? There exists a Y, right? Such that Y is close enough to X, right? We know. For some arbitrarily small epsilon, right? That guarantees that P times Y actually is also inside the budget, right? But the utility of Y is strictly greater than the utility of X. This is a contradiction of the fact that the utility of X has to be greater than equal than the utility of Z for all Z that are affordable, essentially, right? That's the notion of maximization. So this is a contradiction for the case of Z equal to Y, right? As you can see, right? So as Martin basically was intuitively telling us, right? The fact that there is a gap, right? So you're assuming it's inside the budget. It means by local association that there is something nearby that still is inside the budget that is better, right? And strictly so, contradicting the fact that the X was assumed to be a maximum, right? Because being a maximum means that the utility of X is greater than anything that is affordable, weakly so, but better, right? So the fact that there is something affordable and strictly better than X contradicts the fact that X is a maximizer, okay? So by what can I conclude, right? So it concludes that Walras law has to hold, okay? So 2 holds, okay? Everyone is convinced about the proof? Okay, so basically what Martin was doing was great. The only thing is you have to organize it a little bit better, right? So a technique, choose a proof technique, right? So proof by contradiction, right? Do the statement towards contradiction, right? The negation. So basically I have a maximizer, but I assume towards contradiction that is inside the budget strictly, right? Then I do my proof, okay? Got it? Okay, so Walras law holds. Now, the proof of 1 is easy, right? Because essentially, if I change the description of the budget by scaling up alpha and W, if I check my budget correspondence, I quickly see that the alpha being strictly positive cancels out, right? Hence, you know, the description of the budget doesn't change with the alpha, right? So it's the same budget. So this object essentially will satisfy this homogeneity of degree 0. So if I scale basically alpha and W, I'm still fine. Now, important thing about homogeneity of degree 0, it sounds very natural, right? But this is assuming, for instance, that consumers actually pay attention perfectly to prices. Okay, so this has the implicit assumption of full attention, right? This is something that also appears in macro. And for a while, it was very famous in macro because people were complaining since the times of Keynes, John Maynard Keynes, about whether people were or not, in fact, subject to the nominal illusion. It's a cool name, right? Macro knows better names than micro theories, right? So micro theories call it homogeneity of degree 0, very boring. So, you know, macro, instead, John Maynard Keynes called it the nominal illusion, right? So, which is basically a violation of the homogeneity of degree 0. So if people basically homogeneity, the nominal illusion, according to Keynes, was basically the fact that you could create inflation, right? So scaling prices and income by alpha, right? So everything is denominated now with twice the prices, but also twice the income, just because of arbitrary inflation by printing money, right? So in that case, right, I basically print money. I double the amount of money in the world, in this society. I give everyone, twice the money, and then prices double, right? This is the situation. Now, a rational agent will basically say, look, I'm as well as before or as worse as before, right? So now I'm going to spend the same and buy the same objects. But Keynes was claiming that people are slower to internalize the change in prices, but they will feel richer because of the direct transfer of money to you. So you're paying more attention to the income you're receiving than to the prices. He wasn't using the attention name. Attention is a modern category, but he was saying, people won't realize that price is changing as fast as the income they're receiving. Hence, they will end up spending more than before, right? So he was expecting that this income you're transferring them will push, the propension of consumption, right? So Keynes was the first behavioral economist, if you want. So of course, the battle is still there. This is an empirical question. But what I'm telling you is that homogeneity of degree 0 mathematically seems very innocent, but it has, of course, the underlying assumption that people pay attention equally to all prices in the whole vector of prices and to the income in the same way, which might fail. But for now, for the rational agent, this is a substantial prediction of the model, right? So for instance, you can test rationality by actually trying to test the nominal illusion, okay? So if you fail if you actually subject to the nominal illusion, you are not rational, right? You are behavioral, okay? Got it? Okay, great. And, the final thing, and that's what sometimes I don't like Mascolel, Mascolel in the third property introduces a new property, right? Inside the conclusion, right? Which is weird. it should be a different result, but here I'm following him. Maybe we'll change it for different years. But here, you know, he introduces convexity out of the blue, right? And says, by the way, if your underlying preference is convex, mirror image in the world of utilities, the utility is quasi-concave, right? Then basically the image of the XPW is a convex value object, okay? Now, so again, let's draw the convex preference, right? So this is something we're gonna check again and again. So it's better if we do it now with a little bit more care. So who can tell me again what was a convex preference? I mentioned it a moment ago, right? But who can remind me what is a convex preference?
Professor, it's the utility. If the utility representation will have basically convex shaped contour lines.
Yes, exactly. So imagine I have an indifference curve x2, x1, right? I have this thing, the upper contour set of this indifference curve is this, right? Now take two items here, x and y, right? And take here something called z, right? This is the upper contour set of z, this is in the upper contour set of z, right? If I take a linear combination of x and y, right? Let's call it now object x hat, right? X hat is also in the upper contour set of z, right? So this object, as you can see here, graphically is a convex set, right? The upper contour set, right? So now what is a counterexample of convexity? A counterexample of convexity is this object that Mascolet also loves, right? This is the upper contour set here, right? Now take an item, for instance, these items here, right? Take the linear combination of this. This object is not longer in the upper contour set, right? It's below, okay? So this is, of course, not convex, okay? So this is a non-convex object, okay? Good, good. Thank you, Matt. That was great. Now stop sharing. Let's go back to our screen. So again, who remember what is quasi-concavity? So in terms of utility, the definition. So these are things that you have to also check with Maria, right, in general. But quasi-concavity, essentially, this, you know, for the next class, please check it out. You know, is a property of the utilities that we will use in general, right? And it's essentially, you know, it's an ordinal version of concavity, right? And please check what is a convex function, quasi-convex function. That's usually what you find in the internet. And then Kim Border also has quasi-concavity, a concave, okay? So please check this for the class. So we are almost done in the 10 minutes, so I'd rather go through the last part instead of checking these definitions, which are things you can check yourselves, okay? So Karush-Kuhn-Tucker for the UMP. Okay, so essentially, we want now to do more with the utility function, right? So we're assuming now not only that it's going to be locally associated, but also we're going to assume that is actually concave. And in fact, we don't need concavity, we need quasi-concavity, which is the weaker version, right? And in fact, we need it because now we're going to do Karush-Kuhn-Tucker. So Karush-Kuhn-Tucker for this chapter is going to be easier than with Maria because we don't need to check second order conditions, you know. In general, because of concavity, we're fine with just first order conditions, right? The fact that you have first order conditions with a concave utility is enough given the linear budget for knowing that you are getting a maximum, right? If concavity or quasi-concavity fail, then you need to check second order conditions, right? And the extremums or the critical points of your problem are going to be harder to classify, right? You also have the issues of local optimum, and the problem gets scarier and harder. For us, luckily, and throughout this chapter, we are just going to assume now going forward that the utility is quasi-concave, okay? And there is a reason for this and why we can do it without shame. And I'm going to show you at the end of the chapter, there is a famous term, the Afriet term, that basically shows that with final experiments, there is no way to differentiate between locally associated and continuous utility function and basically rationalization by a different quasi-concave utility function, right? So in other words, concavity turns out to be non-testable, right? The same as continuity. So surprising, right? We're gonna go to that chapter, to that results at the next class, which is called the average theorem. But essentially, we can assume concavity without shame because turns out that for rationality, concavity is a non-testable condition, right? So because it's non-testable, it means that it's a technical condition. Okay, great. So with concavity, we can focus on Karish-Kuhntacker only with first-order conditions. So it's simpler. So this is a formulation that's more practical for consumer theory. Of course, the full Karish-Kuhntacker for general problems, you have to learn from Maria. But for me, it's a simpler version, right? So take a Lagrangian, utility plus the Lagrangian of the constraint being the budget constraints, W minus P times X, inner product. Now, because I'm allowing for corner solutions, I have the complementarity conditions, the slack conditions, the partial derivative of the utility at a possible solution is basically deriving with respect to XL, right? So this should be actually X, this is a typo here, is less than equal lambda, which is the Lagrange multiplier. It's another variable you're looking for, multiplied by the price of L, okay? And again, if you have a solution that is not zero, this will hold with equality, right? But in general, we know that it can hold with a strict inequality or with equality. Now, how do we know? We add the complementary slack conditions, the slackness conditions, and this basically tells you that there is a bracket here. Again, this is a typo here. You have that XL multiplied by the parentheses or brackets of the partial, or basically the first order condition. So this means that this has to be zero. Either the condition of the first order condition here holds with equality, right? Or the XL of the particular coordinate has to be a zero, right? So in other words, if the first order conditions hold with the strict inequality, it has to be that the XL is a corner solution, right? So usually this is going to be zero, okay? And in the cases where the first order conditions holds with equality, X can be positive or can be zero, it doesn't matter, right? So XL, the coordinate XL can be anything it wants as long as it's non-negative whenever the first order conditions holds with equality, okay? And of course, the budget constraints have to be that W minus P times X is greater than or equal than zero. At the same time, there is this slackness condition that the Lagrangian multiplied by the budget constraint is equal to zero. So here again, notice that when we assume local association, right, the budget is always going to be equal to zero, right? What does it mean for lambda, for the Lagrangian? It means that we can always assume with local association that lambda is strictly positive, right? So from now on, lambda can be assumed to be strictly positive. So the Lagrangian can be assumed to be strictly positive because of local association, okay? So when is the lambda zero? When of course, when the object here is different from zero. That means for cases where you have satiation points, okay? So you have some interior inside the budget solution, then the lambda is imposed to be zero, okay? Because it's not active. The lambda is not active. Now this is a system.
But that is not going to happen, right? With local association. Okay.
With local association, it never happens, and that's why we can assume that the Lagrangian is always strictly positive. Okay. So from now on, you can think of the Lagrangian as strictly positive. And now, you know, this is a system of nonlinear equations with L+1 unknowns. L, demand entries, right? So for the L goods plus the Lagrangian. And I told you, right, that in practice, people usually never recover the lambda value. Usually it's not point identified as well. So you never get a single value. So usually we try to avoid it, bypass it, right? And then what we really are after are about the demand values, right? So even so, this system is fully solved when you solve for the L+1 variables, including the lambda. We're not in a math class. So if you solve my problem and you give me the values of the demand, right? That do not depend on lambda, but only depend on prices and income, right? That's a solution. So you bypass the lambda, then this is a solution for me. Do you understand? So in that sense, you know, we're living more at ease than in a math class. Okay. Again, as I mentioned, and also Martin realized, you know, by local association, we know that the consumer is on the budget hyperplane frontier. This means that W minus P times X prime, X star is equal to zero. Now, making the connection with undergrad, as I told you in the summer, imagine that you have certain utilities that in fact have interior solutions, like the Cobb-Douglas, right? In that case, you can actually simplify even more the cross-conductor conditions and make them basically what is called the marginal rate of substitution, which means that the partial derivative of the utility at XL divided by the partial derivative of U at XK is equal to the inverse ratio of the prices. So this of course you learn from undergrad, and this has a nice intuition that the slope of the budget line, right? So minus P1 over P2 is essentially, equal to the marginal rate of transformation, which is the slope of the indifference curve, right? Usually this is called the marginal rate of substitution. And this is very important, even if it's more basic in terms of theory. This is a very interesting insight. It's telling you yet another phase of utility maximization in the world of budget constraints with linear budget constraints. And it's telling you that you can understand rationality using derivatives, right? And in fact, it's telling you that maximizing a utility function means that you have this marginal rate of substitution, being equal to the relative price. So in other words, this means that any optimal object will only depend on relative prices, right? It never depends on the level of the price. And that's another phase of the homogeneity of degree zero. So because money illusion is not at work, right? The only thing that matters is the relative prices, not the absolute prices, right? So the only thing that matters is the terms of exchange, right? So how, the relative price of a good, right, is how many apples do you exchange for an orange, right? That's the relative terms of exchange, the ratio of PL and PK. And what this is telling you is that the maximizer, the rational agent, is trying to equate the rate of substitution in terms of utility, right, to these relative terms of exchange, which is amazing, right? So it turns out that maximizing a complete and transitive preference gives you this facet in the world of first order conditions that essentially tells you that the consumer ends up working in the margin, right? So they try to equate the marginal rate of substitution to the relative prices, okay? And of course, all the intuitions from undergrad work here. And what I want to tell you basically is that this is how we connect the more abstract theory of complete and transitive consumer behavior to the first order conditions, right? From marginal rates of substitution. Now, why did we go through the trouble of doing the more general complete and transitive with preferences binary relation, right? It's because this model that we studied until this point, the one without differentiability, without utilities, is more general, right? So it's gonna be the same even if you assume your choices is discrete, right? Even if you have a set of cars or insurance, right? As opposed to fractional trading. So the price we're paying for getting more intuition and being able to differentiate and so on is that our choice set is more specific, right? And is this Euclidean space. So in that sense, we're gaining more intuition, and rationality has more intuition here because we're studying a more constrained environment, right? So it's a smaller choice set that we were used in the previous chapter, okay? So did you understand that part? Else, let me know, right? So basically, I'm just telling you that in this particular world, rationality has this additional intuition, right? Of the first order conditions. But in general, it doesn't have to be, but we know that guard and warp are the, more robust implications that always work, okay? Now, okay. So here, I'm gonna stop. I'm gonna stop recording as well, and we're basically done.